Hello, y'all. Thank you for coming to our last Gen Chem study session of the semester. We glad you're here. And Dr. Taylor, please take it away.
Fabulous. Fabulous. So yes, I do apologize. I was mostly trying to make sure that my computer will not miscellaneously update on me. So I am a little bit behind. But basically, we are going to talk about what we are doing for exam 4. So where is the stuff I did this morning? That's about right today. There we go. But this is from today. Good. In general, what we are talking about in exam 4 is, I usually just like to go ahead and say that it's chapter 15, 16.4, and chapter 19. Now, you might remember that we already asked y'all some entropy questions out of chapter 15. So there were a few things that we already did on exam 3. The thing, though, is that almost everything you already learned about entropy is something that is a useful concept to bring forward. So while we won't ask you directly those same questions about entropy that we asked you on exam 3, the overall arching idea of what is entropy and how would you know that entropy is increasing or decreasing is still valuable, is still useful information. Because when we started getting into chapter 15 in more detail, that's when we could start to talk about things like spontaneity and dealing with Gibbs free energy and that relationship with whether a reaction is endothermic or exothermic and its change in entropy and the temperature. So granted, we had an equation for that, but we could also represent that equation in a conceptual manner. So while on one hand, yes, you could definitely tell me that there are things about entropy that we would likely not ask you again because we already did. A lot of those concepts still come forward. So that's going to be my general byline for chapter 15, 16.4, chapter 19 is you pretty much need all those pieces about entropy coming forward. 16.4, honestly, a lot of times 16.4 flows so seamlessly from chapter 15 that you may not have actually realized what parts of that were actually not technically in chapter 15. But chapter 16.4, that section is basically anything that related delta G to K versus Q considerations, delta G standard to K. All of those things that brought equilibrium to thermodynamics, all of those considerations are in 16.4. Because this is that part where we went a little out of order of your textbook. So your textbook does equilibrium in chapter 16, but thermodynamics in 15. So we hopefully seamlessly knit them together, and you really might not have actually noticed where that information is, because applying equilibrium to thermodynamics works really well, but that's all what the 16.4 section is about. Then last but not least is chapter 19, and this one is all electrochemistry. So this has been what we've been doing recently. So this is everything from balancing reactions to predicting oxidation reduction to dealing with the Nernst equation. Sorry, that's my can I do the Nernst equation from scratch? I did it this morning. That's what I'm looking for. Nope. Actually, while I'm struggling to write the equation from scratch, I have a draft of y'all's potentially useful information sheet. The only thing that's really missing on this, I can show you, is down here. We had to have a little conversation because my laptop, ironically, is kind of notorious for having formatting issues. So I couldn't see that this was the log of Q. It should be the log of Q. And apparently that was not just my computer. Apparently that is everyone's. So Dr. Diekman is putting the finishing touches on this sheet. It should be out shortly. But what you might notice in here is we do have a variety of new equations in here. So things like our delta G standard relating to our standard enthalpy and our standard entropy, delta G standard relating to K, all of that good stuff. And then down here at the very bottom, we have more things that relate more to thermodynamics, dealing with our standard E cell and dealing with Q or K. There are also a couple of definitions up here because we will need things like Faraday's constant, F, the fancy cursive F is up here. Our various gas constant options are over here. What else is up here? Oh, the definition of a volt. And the definition of a Coulomb is what that one is, which we may also get into. So this is not posted yet, again, mostly because if you didn't watch me draw in the letter Q right there, that just has to be fixed, which is coming shortly. This is one of those times where honestly, I'm very thankful that I am not in charge of formatting this particular page, because I really don't know how Dr. Diekman got all of that on one page. I would not have done that by now. If I was in charge, that would definitely be 2 pages, because formatting is not my strong suit. Anyway, so balancing, predicting, I'm just going to write equations on here because that'll come up at various intervals. We're also going to have, so we've been doing galvanic cells, which are also known as voltaic cells. That's the same idea, that they're both spontaneous. And we are therefore getting into electrolytic cells, which are non-spontaneous. And then we will also be into electroplating. So this is the one topic that I needed to double check. It is on this current upcoming exam, but electroplating might very well be something that we didn't make onto the spring exam, spring 23 exam. That is your old exam. I'm trying to remember, and I honestly have not looked at it yet, but basically electroplating is the very last thing we do in chapter 19. So because it's the very, very last thing, there are occasionally times where electroplating does not make it on the exam. It will make it on the exam for your exam this Saturday. We have plenty of time to cover it, don't worry. So my main goal before I took questions was to make sure we chatted a little bit about the different things that were coming up and point out that there is a new potentially useful information page coming, even though it is not quite posted yet because of that little Q right there. So any questions that people would like? Has anyone put questions in the chat yet? Ask that question.
Yes, ma'am, we have 2. Can you explain what's exactly on the exam, please? Are we going to cover all chapter 19? I think you went over that a little bit. And then can she go over 7, 15, 19, 20, and 27 from last semester's exam?
Oh gosh, give me those numbers again. 7,
okay.
15,
19, 20, and 27.
Okay.
And that's it for now?
Okay, cool. So let me, hold on. Basically, what I'm going to do very quickly is scroll through and see if there's anything major in 19 that we don't do. Nernst equation. Oh, we do not do concentration cells. There's a couple of little things we don't do. So concentration cells are a really specific application. They're really not that bad. But basically, in a concentration cell, both of your half reactions are the same. And we decided that while it was a really fascinating application, it was an application that we didn't need to cover. So we don't actually cover concentration cells, but we do cover the Nernst equation. So this is one of those odd times where We do cover the first part of 19.5, which is spontaneity of redox reactions under conditions other than standard state. That's the Nernst equation. There's just a specific application of the Nernst equation that we do not do, but we do the Nernst equation. So 19.5 is on the exam. It's just not the concentration cell part. Batteries is another one of those situations where I like to cover batteries in class because it is possible that we will reference something like a lead storage battery, and that we might mention still anodes and cathodes in a particular setup of a kind of battery, but we are not going to ask you like which of the following reactions is the correct reaction for a lead storage battery. Not a thing that we're going to do. So usually in class, I will cover batteries very quickly, mostly to point out that, you know, when we talk about things like a AA battery, or when we talk about the battery in your cell phone, those are still batteries. They are still electrochemical reactions happening in there. But, you know, we don't, like, our cell phones don't slosh because there aren't like two different beakers hiding in your cell phone. So there are other ways to still do electrochemical reactions without the two beaker setup. A lot of times they involve pastes so that they are kind of moist, but not super moist. So there's lots of different ways to do them. But anyway, so batteries are the other thing that kind of gets like a hand wave. Again, useful to at least be familiar with some of the language, just so if we write a question that does describe a battery, you don't suddenly go, whoa, no, I've never heard of batteries before. But again, we're not going to have you do some sort of matching thing with that. In electrolysis, we will do molten and we will do water, and we will do quantitative applications. The electrolysis of an aqueous sodium chloride solution, unless that's just a fun example, if there's anything weirdly specific about this one, we will assume that things are normal, essentially, in electrolysis. We will assume that electrolysis, which is a electrolytic cell, can either be done with water or without water, and those are really the only two things we're going to assume. And then corrosion really falls under the same idea as batteries. Corrosion's kind of difficult to write like a good question about exactly, but again, corrosion is something that, because it is an oxidation reduction reaction, it is certainly something that we could reference. We could certainly talk about the corrosion of iron. We could talk about the corrosion of really almost always do iron, just because stainless steel and other things are most common out of that. And the hard thing is that usually when you're talking about other oxidation reactions, usually we have fancy names for some of them, like the fact that the Statue of Liberty is green is an oxidation reduction reaction, but because that's an art thing, and the fact that that copper compound is green, and they want it to be green, like the Statue of Liberty is not supposed to be a shiny metal color. The Statue of Liberty is supposed to be green. They call it a patina. So they don't refer to that as corrosion like it's a bad thing. They refer to it as a patina because it's supposed to look like that. Whereas corrosion is something that we don't want in particular, because it's usually metal oxidizing into some form that's not as valuable to us. And we usually think about rust, because nails rusting go from a nice hard metal that is a little bit malleable and a little bit bendy to rust that is very brittle and very flaky and not great for holding things together. So again, corrosion and batteries are the two things in chapter 19 that I would argue have value both for some vocabulary terms and just for some ideas of applications. So it's definitely possible for us to still use some of those words, but Like, you don't need to like make flashcards based on them. You just need to be okay as long as you've heard some of those words before and know that those apply to oxidation reduction reactions. That's really all you need in there. And that really has more to do with the fact that, like, I mean, we could ask you guys to memorize things out of there, but not as much fun. One of the other things in chapter 19 that you should be at least somewhat prepared for. So I know in my class, because I would like y'all to be able to see what I talk about, I usually use this standard reduction table that is much smaller than the one in your textbook. And it has value and it has its uses, really honestly being that it's small enough that I can put it up and you can usually see it, or at least if I start to gesture just particular things on it, it doesn't look like it's just a bunch of lines. As opposed to what we usually give y'all on the exam is we usually just take the table out of your textbook, which is this thing, but in your textbook, they go ahead and do this lovely thing where they, come on, where are you? Standard reductions, where they give you some arrows and we take those arrows away. So in your textbook, your standard reduction table has these arrows that say increasing strength as oxidizing agent, and a little arrow here on the left pointing upwards, and then on the right hand side it says increasing strength as a reducing agent and an arrow pointing downwards. And we do remove those arrows, so that's why in my Microsoft OneNote it just has a list of half reactions and their voltage. So this is much more likely what we'll actually give you. As you can probably tell, it's a really hard to read, but I nabbed it just in case I needed it. But otherwise, when I can, I have a tendency to use this smaller one just because that way, first of all, I can get the fluorine reaction and the lithium reaction on the same page, and you possibly can actually see this F2 here on the left in green and this Li down here on the bottom. So that's the table that I will use as much as possible, honestly, because you can read it as opposed to this scrolling thing here. But I will give you a couple of pieces of advice because this table here is so long. There are a couple of things I do actually recommend on this table. One, now this one's, glad I went ahead and said yes to go ahead and turn my camera on. In case you're curious, I got my hair cut this afternoon because my hair was really bothering me. So I got my hair cut, which is why it is all over the place. But that means that we did turn my camera on. I'm glad, because this will actually be useful. So if this page is supposed to be all of your like little teeny tiny writings, one of the hardest things is this table is really not designed very well, honestly. So it's really easy that instead of going just across the line, you might accidentally go at an angle downwards or at an angle upwards. And so it's kind of easy to accidentally misread the table. So what I actually really recommend you do is you grab a second piece of paper, because you have two pieces of scratch paper attached to your exam. They've always been there. They will continue to be there. And you can actually use that second piece of paper as a straight edge. So that way, when you're trying to find a reaction that goes all the way across, you use piece of paper number 2 to basically keep your place. So that way you can read the table a lot cleaner, a lot easier, is way better. Highly recommend. When I actually use this, I will actually do that because 1, I think demonstration is really helpful, and 2, it's easier. For the record, when we did exams online during the time of which we do not speak, I recommended people use sticky notes on their monitors because I think that straight edge is really useful. One more thing about this table I think is valuable and useful. So when it comes to electrolytic cells, one of the tasks, and just one of them, so there's lots of different questions we can ask, but at some point, we're going to ask you guys about aqueous, electrolytic cells, and aqueous. And the really bizarre thing about those is you have to consider water reactions. So we'll come back around to this idea, but what I'm going to do right now is I'm just going to underline the reactions I care about. So, and the beautiful thing is one of these is at positive. Come back here. Oh, come on now, OneNote. I shut down the computer. I turned the computer back on. You and I were supposed to be friends today. There we go. We'll just use a highlighter. Why not? So one of these reactions that involves water is at positive 1, 2, 3 volts. And that's usually fairly straightforward. 1, 2, 3. And then the other water reaction that we need to consider is not as nice and neat and straightforward, but is down here and is at the negative 0.83 volts. So those are the two reactions that I would recommend that you either memorize or at least be cognizant of which water reactions you care about, because water does show up in a lot of different places on this table. And so occasionally folks will get kind of bogged down or just nervous, and they will have problems finding the reaction that they care about because this table is really small and water shows up often. So those are the two that I would recommend. There's a water reaction down below, negative 0.83 volts, and a water reaction up above that we might care about at positive 1, 2, 3 volts. So I did see the person that asked about the questions, the old exam. Depending on time, I'm going to again try to save these for that video afterwards. So these are definitely, we'll note, but these are those old exam questions that I'm going to aim to do later. So any other questions so far?
Yes, ma'am. We have 2 more.
Okay.
For number 5 on last year's exam, how would you calculate Br minus bromine minus negative?
Okay.
Is it just negative 1.066, or do we need to divide by 2 because there's a 2 as the coefficient? Okay. Oh, sorry.
No, fine. What else?
Okay. And the second one, it was questions 1, 5, 9, 16, and 18, and 23 from the previous exam. And yeah. And that is all for now.
Okay. Let me actually grab that bromine question because I have a feeling I know what that one's about. And that might actually be useful of a conversation. Actually, no, I'm not. Change my mind. So I was like, wait a minute, I came prepared to talk about things. So what I'm going to do, so again, you're welcome to put old exam questions in the chat. And I am happy to do them, but I will be doing those in a follow-up video. And it looks like I will be doing half of the exam. 1, 2, 3, 4. Yeah, a third of it. That's fine. But what I'm going to go ahead and do is I'm going to go ahead and pick 2 half reactions, and we are going to talk through one, how you know which one is oxidized and which one is reduced. And then we'll also talk through basically what would happen if we ran the reaction backwards and what that might look like. So I actually did pick some kind of wonky ones, but I did that on purpose. So I chose, because my nice cute one is a little too streamlined. Okay, so first of all, I'm going to pick, it is this reaction, but it is chromate plus 4 waters plus 3 electrons goes to chromium 3 hydroxide plus 5OH. And again, that number there that you probably can't see is negative 0.13 volts. And then the other one that I picked is shorter to save me some time. Just manganese as a solid going to manganese 2 plus 2 electrons, and it's a negative 1.19 volts. So, right? Popcorn. So one of the things that is a little bit strange about voltage is we do have to do things. So if we were just going to, so what we're going to do is we are going to go ahead and say that this is going to be a galvanic cell, also as a voltaic cell. So we can go ahead and say that this is a voltaic cell, just to give us some different language. But that means it's spontaneous. And what we're going to do from here is we are going to go ahead and start, and we are just going to calculate the E-cell standard for this. Now, the thing is that when we first learn about E-cell standard, we're like, all right, we are just going to pull reaction. We're just going to pull the values off of the table and work with them off of the table. And I think the person's asking about the bromine. One of the things that's strange about that, because the first time you hear that, you're like, all right, I'm with you. But then when you start to look at these, oh, I did this backwards. Sorry, realized that I did not write that as a standard reduction, but I wrote the standard reduction value. We're doing just fine. There we go. So both written as reductions. But what you might notice is that those electrons don't actually match. So granted, bizarrely enough, we don't care about that if the only thing we need is E-cell standard. We don't care. It's good to notice in case we need to do more with those. But the strangest thing is that voltage in these half cells is an intrinsic property of these particular compounds or elements. So intrinsic properties are things like if we point to a metal and we say that the metal is shiny, it doesn't matter how much metal we have. It can be a small amount that's shiny. It can be a large amount that's shiny. And shiny is the only thing that we care about. It doesn't matter how much of it we have, we get the same out of it. Now, most of the time that we've been doing various calculations, anytime we've dealt with entropy, enthalpy, delta G standard, all of those, whenever we've done those, have always been in kilojoules per mole, sometimes joules per mole, or joules per mole, or joules per Kelvin per mole, but this per mole was hanging out in there. And the thing is, we kind of ignored that, but this part of this per mole is technically per mole of the reaction. And what that meant is that means, I should say means, because we can still do some of these, is if we are dealing with something relatively straightforward to make my life easier, we're just going to make all of these gases, 2 there and 2 there. So if we're doing something, we're just going to say these are all gases. And I say that this reaction here has a, we'll go with an enthalpy value of negative 56 kilojoules per mole. That is per mole of reaction. And so that way, whenever we did enthalpy, we could come in and we could say, I'm going to multiply this entire reaction by 2, and now I have 4 hydrogen gas, and now I have 2 oxygen gas, and now I have 4 waters, still as a gas. I'm picking that. And my enthalpy value would also be multiplied by 2. because this was per mole of reaction, and whatever we did to the stoichiometry of that reaction, we had to do to the value of delta H. And that goes for delta S, and that goes for all the pieces, all the parts, for our value of Gibbs free energy. What those are goes together. Now, here's the weird thing. That's not necessarily true when we do information with voltage. These are intrinsic properties. So those are just volts. They're just volts. They're not volts per mole. It's just volts. Now, we'll get to that in a minute. So it's just the voltage. So that is an intrinsic property of that half cell. Now, keep in mind that that idea of an intrinsic property, we are still doing things because it's the standard. We are still doing things at 1 molar concentration and at 1 atmosphere. So there are still pieces that matter. So it's not like we can just do this with any particular combination and get those values. But we don't take that voltage and divide it by 3 so it's per electron. We don't do that. That voltage just belongs to that half reaction, no matter the stoichiometry. I will point out now that when we do go to comparing things to Q, or when we would go to comparing E to delta G, and now we do have something in there just to make these bigger. So when we do then go to situations where you're like, whoa, delta G is in per mole. What is how are we going to deal with that? Realize now that this in factor in here is going to help me take care of that, because this in is my moles of electrons transferred. So there is still going to be information to basically say, so which electrochemical reaction are you talking about? And essentially, what is your stoichiometry? So whenever we do go ahead and make comparisons between something with a voltage and something that has that, then the stoichiometry matters, we basically put in that stoichiometry factor so that we can make that comparison. So that's part of why that's in there, is to make sure that they actually can be compared to each other, because delta G and delta G standard care about the stoichiometry of the reaction. So if we're going to compare delta G standard to E cell standard, we have to add that factor, which is why it's part of the equation. So we get to make those comparisons because the equations take those into consideration. I'm going to hope that's helpful. Every once in a while, I have those moments, and this is one of those where I'm like, I really wish I could see people's faces to be like, did I make it better? Did I make it worse? I'm not sure. But we're going to go ahead and assume we made it better. And go ahead and move forward, because I didn't actually even do the first problem yet. Great. So the goal is to calculate E cell standard. So what I'm going to do is I'm going to go ahead. I have these 2 reactions. Again, if this tiny little thing was legible, you could have just pulled them off of there. I honestly just rewrote them out so that you would know what we were talking about and you could actually see them. So since I want to calculate E standard of the cell, what I'm going to do is I'm going to go ahead and take another look at that potentially useful information. And my potentially useful information has an equation on here. And so I'm going to use that. And the equation that's on your potentially useful information page says that my standard for the E cell is equal to the standard reduction potential plus the standard oxidation potential. Your textbook does not say that. Your textbook says that your standard E cell is equal to your, I'm going to get this correct. Yes, I am, cathode minus anode. So I have managed to, I think, thoroughly confuse my class by trying to show off both of these. So I am going to pretend like this doesn't exist because it's not what's on your potentially useful information page. And if you have questions about it, I will answer them. But otherwise, I'm just going to acknowledge the fact that this is what is in your textbook, but that's not the thing that is on our standards, is on our potentially useful information page. So I'm going to ignore it. So this means that I want the standard reduction potential and the standard oxidation potential, which means between this blue equation up at the top and the black one down below, I need to know which one is oxidized and which one is reduced. So this is the part where in our standard reduction table, things closer to the top of the table or the things that are more positive are more likely to be reduced. The things towards the bottom are more likely to be oxidized. This is the reason, honestly, why I like my little table, is because here we can go ahead and see fluorine gas. And whenever we look at a periodic table, nope, don't have one over there. Whenever we looked at a periodic table and we would talk about things like electronegativity, we could go ahead and point to fluorine and say that fluorine was the most electronegative element. It was going to want electrons no matter what. And so seeing fluorine at the top of the standard reduction potential table should hopefully make sense. Fluorine is something that very much wants electrons. It is going to be most likely to accept electrons and most likely to be reduced. Versus hanging out way over here, lithium is one of our alkali metals, and it is much more likely to be oxidized. It does not really want its electrons. It would much rather ditch them and be positive. So everything in your standard reduction table is written as a reduction, but your fluorine is more likely to be reduced. Your lithium is more likely to be oxidized. So just orienting yourself on the table, it can be helpful to think about periodic trends. The one thing I would warn you about is these don't follow periodic trends perfectly. Also, there's a lot of stuff that's in the big table. So it's just nice to kind of orient yourself, which one is the top, which one is the bottom, based on chemistry that we've done before. So all of that being said, my reaction in blue that is more positive, I know it's still a negative number, but it's more positive than the other one. This is going to be the one that is reduced, or is my reduction reaction, and this one down here is going to be my one that is oxidized. Since they're both written as reductions, that means that since I wanted a standard reduction potential, I just get to use this negative 0.13 volts. So my standard reduction is 0.13 volts. Plus, now this is the one where I have a bit of a problem because this reaction's written as reduction, but we just said it gets oxidized. So what we're going to go ahead and do is rewrite this, or at least I'm going to rewrite this, to notice that this should be an oxidation potential. If this is really an oxidation potential, then I need to change the sign. Because I flipped the reaction, so since I've now changed my reaction, I don't have a standard reduction potential anymore. I now have a standard oxidation potential. So I'm going to go ahead and put that in there. Positive 1.19 volts. Here's my calculator. So this is a positive number, and that's great because I should have a positive number. I should essentially have, anytime you have a galvanic cell or a voltaic cell, those are both spontaneous, my voltage should be positive for those. So that is equal to my standard E cell. Now, we could do this differently. So there are a lot of different things that we can do. But since I have these two reactions, and we just talked about these being spontaneous, I could go ahead and I could also consider, so actually, yeah, no, we'll just keep going. I could also consider, what if this was a non-spontaneous reaction? What if I forced this to go backwards? So we have a couple of different ways of writing that out, but the main thing is that if we're going to do this as something that is non-spontaneous, so if we were going to do this as a non-spontaneous, what we are going to do for non-spontaneous is these are called electrolytic cells, or sometimes electrolysis. When we do these, one of the things that comes with these is you usually have to apply a current because the reaction does not want to go that way. So therefore you have to force it to. So usually you install a battery. Usually you're installing something to show which way this reaction is going. When we do electrolytic, we're basically going to force the reaction to happen so everything runs backwards. Now, one of the weird things is we could just flip these two things around, essentially, and be like, all right, no worries. That just means everything runs backwards. So my reduction reaction is now my oxidation reaction, and my oxidation reaction is now my reduction reaction. Everything flips. So in a perfect world, you would just have an E cell standard of negative 1.6 volts because you just flip things around. But so actually let's do an example of that, but let's do an example of that with these guys where it's a little bit more straightforward. I'll get there. So if we're going to do something like this, what we usually do is we can run molten cells. When we run molten cells, what we do essentially is we go ahead and we say that you have a molten salts of FeCl3, and you have both electrodes hanging out together, and we are applying a current. This is not my best work, but this is attached to a battery somewhere or the wall, you know, whatever. And because this is just molten iron 3 chloride, we get to do a couple of things with this. One, you actually know what your reactants are because molten iron 3 chloride is all we're starting with, which means that you begin your reactants have to be Fe3+ and Cl- because that's all you begin with. Those electrodes that are in there are some random piece of metal that are not necessarily these same pieces. So we're not going to pretend that those particular half cells might be there. We're just going to say, if it's molten, then I am starting with whatever those pieces are. I am starting with Fe3+, I am starting with Cl-. Because that's where I'm starting, I can go ahead and look at my table to figure out where I could potentially go from here. So this is the part where I actually do get to make some sort of decision. What is more likely to happen? So I've got two options for iron 3. I've got iron 3 going to iron, and I have iron 3 adding 1 electron and just going to Fe2+. So no matter what I'm going to do, my iron 3 has to have some sort of reaction. But here, unless I'm told otherwise, my iron 3+ has two different things it could potentially do. Now, it has to get reduced. It has no other choice. It's being applied a voltage. My iron 3+ cannot be created. But because it's getting reduced, I can still go ahead and pick the more likely to be reduced option. So for what could potentially be happening here, I'm going to go ahead and select the, out of two different options for my Fe3+, I'm going to pick the option more likely to happen, because basically all those electrodes are just hanging out together. And my Fe3+ is going to gain 1 electron. That's my reactant. It's the only thing it can do. And go to Fe2+. My other reactant is the Cl-. Now, the weird thing here is my Cl- is showing up, but it's usually a product. So starting with Cl-, starting with the chloride anion, the only thing that this can do is be oxidized. So the reason why electrolytic cells are kind of strange is because my chloride reaction is higher up on the table than either one of my iron reactions. But my iron reactions are going to be what's being reduced. My chloride reaction is actually going to be oxidized. This is an electrolytic cell. Even though the more likely thing would be that a chlorine reaction would be reduced and an iron reaction would be oxidized, that's not happening here. The opposite is happening. We are applying a current, we are making things happen, we are forcing a non-spontaneous reaction to occur. So because we are making a non-spontaneous reaction occur, we are going to go ahead and get my chlorine to be oxidized. So oftentimes when we deal with molten situations, we usually ask essentially, what are the products or what are the potential products? So trying to come up with like what's going to happen. And it is a bit tricky dealing with the iron reaction, because even though everything is running backwards, if you have two different ones to select from, you have to remember that we're just basically putting a current and we're just applying voltage into this molten salt. So even though we are making things go backwards, we're still going to have the easiest thing possible happen. So even though I have two different iron reactions to pick from, we're going to have the reduction be still the most likely reduction possible. So this is one of those things where if you're either like trying to get a kid to eat vegetables, but they have two different vegetables on their plate, they may go ahead and do what you forced them to do, which is eat their vegetables. But if you gave them an option between carrots and broccoli, and they really like the bright orange carrots, and they don't like the green broccoli, they're going to pick a vegetable if you force them to eat them, but they're going to pick the vegetable that they like. They're going to pick the vegetable that's easier for them to eat. They're going to pick the carrots. Same thing's happening here. We're going to force this reaction to happen. So we're going to force that chloride ion to give up an electron, even though it doesn't want to. We're going to force that iron 3 to pick up an electron, even though it doesn't want to. But that iron 3+ essentially gets to choose if it picks up 1 electron or if it picks up 3 electrons, because we don't really have a great way to force that to happen. In this particular setup, I should say. So that's molten reactions, which means, so let me go ahead, stop there and ask for questions and see how we're doing on questions.
Okay, so I think there's only one more. Can you explain how delta S for the surroundings is directly proportional to the enthalpy of the system, and how delta S in surroundings is inversely proportional to temperature? Also, if delta H is positive and delta S is negative, would the reaction be spontaneous in the reverse direction?
Great. Okay.
Right.
So we'll go ahead and switch gears a little bit. So these are going back to some of the definitions from the beginning of chapter 15. So this was dealing really with how we get back to dealing with system and surroundings. So first of all, let's go ahead and state the second law of thermodynamics. Because believe it or not, this is actually why we do this, dynamics. I was having a real problem with spelling this morning. So the second law of thermodynamics says that the change in entropy of the universe increases in a spontaneous reaction. And that delta S of the universe does not change, would be equal to 0. Does not change for an equilibrium process. So delta S of the universe is all well and good, but incorporating the universe, that's kind of a lot of stuff. And when we say it's kind of a lot of stuff, what I mean by that is the delta S of the universe, or the change in entropy of the universe, is trying to take everything into consideration. So that's the change in entropy of the system, which for us is usually the reaction that we're studying, and the change in entropy of the surroundings. And that's everything, essentially. It's the reaction that's taking place and everything else around it. Surroundings is everything else around it. So the thing is that when this thing in blue, eventually we rearrange and make a lot of restatements, and we wind up with this guy. Now, the reason we do this is because dealing with the system, measuring things about the chemical reaction, is easier, more straightforward, easier to control, easier to deal with, easier to talk about as well. So while we could discuss the universe and the system and the surroundings, we would honestly like to get rid of most of those and just talk about the chemical reaction and ignore the surroundings and forget about the universe for a while and just concentrate on the thing that's happening and the thing that we care about. So the thing is, in order to go from the statement in blue about the universe and the system and the surroundings, all about entropy, to Gibbs free energy, enthalpy, temperature, and entropy, but only of the system, everything about the system, we have to make a couple of different considerations. So one of those considerations is to essentially relate the surroundings, the entropy of the surroundings, to the system. Well, one of the things that we know is that if you heat something, if you increase the temperature, you can increase the entropy. So this is one of those times where I realized it was like almost an hour ago, but when we first got started and I was like, so there are things about entropy that's still nice if you knew what was happening. This is one of those times. Heating things up gives them more energy. When they have more energy, they have more microstates. They have more options available to them because they have more energy to get there, more potential to actually get there. So because of this, we also know that when delta H of the system is negative, that is, it's exothermic, that means that if I had my lovely beaker with the system inside of it, if it was radiating heat, I can at least make those red, maybe. Essentially, in an exothermic reaction, my negative delta H means I'm heating up the surroundings. So that's where that one comes from, is that my delta S of the surroundings is proportional to negative delta H of the system. That is, when I have an exothermic reaction, it increases the entropy of the surroundings. And you could certainly say the reverse as well. You could say for an endothermic reaction, things getting colder, I would also be decreasing the entropy of the surroundings. So that's how we get that statement. It's the fact that because we can think about a reaction influencing the heat energy around it, we can therefore make statements about what that has to mean for the entropy of the surroundings. More heat out, entropy of the surroundings is greater, goes towards more disorder. Heat goes down or it gets colder, your entropy of the surroundings should also decrease to go along with that colder temperature. So, first part. The other part is a little stranger, because the other part is delta S of the surroundings. The change in delta S of the surroundings is inversely proportional to the temperature. Now, here's the thing about this statement, and I'm actually going to grab my notes for a minute because I use this analogy and I like to give credit for where this analogy actually came from. Maybe 15. It'll come up eventually. So this analogy actually comes from a different textbook. It actually comes from a textbook that is used for physical chemistry, which is a junior or senior level course. I forget which now. But it is just a lovely statement because basically, so this is from Adkins Physical Chemistry 7th edition, Peter Adkins and Julio de Paula. So basically what this says, now that I've at least put up on the screen, if you really want to read that whole thing, you can go back and pause the video. What this is really talking about is basically you get more change or more drastic change, I should perhaps say, at lower temperatures. So essentially, when you have really low temperatures, you don't have a lot of entropy. So if you are in a library, in a quiet library, and somebody sneezes, that sound is really loud because everything around it is so quiet. That's the idea of more drastic change at a lower temperature. At a low temperature, there's so little energy that any change in entropy, any change to temperature is big because of how low everything is. Conversely, if you had that one single sneeze taking place on a busy, crowded street, there's traffic going by, there's cars, there's people, who knows what all. That one single sneeze might not get noticed because there's so many other things happening. That one sneeze, well, it is still a sneeze and it still makes a sound and it is still an event. It's much more difficult to notice it when you have so many other things happening. When the temperature is high and you have so many different energy states available to you, noticing that change in entropy between a small change at a high temperature is much more difficult to notice than a change at a lower temperature because of the entropy you have at low temperatures versus high temperatures. So the thing I think that usually happens, and honestly, it happened to me the first time, is when you first see the statement, because this one is in the notes somewhere, delta S of the surroundings is proportional to negative delta H divided by system divided by T. The thing is, when you see that, the instinct is that because you can write that as one statement, that conceptually those two things go together. And the truth is you have to think conceptually about the enthalpy idea and then think conceptually about the temperature idea, because they are both related to the change in the surroundings, but conceptually how you get there is not all in one go. You have to think about the enthalpy and the temperature separately. I think there was a second part to that question. Scroll back up. Oh no. Oh no. There we go. Oh, okay. So delta S of the surroundings proportional to negative. There we go. Negative delta H of the system divided by T. And then the other question was if you have a endothermic reaction and something that decreases in entropy, would you basically say that it is spontaneous in the backwards direction? Yes. So keep in mind that we usually say that this is non-spontaneous in the forwards direction. And the forward direction is what we typically say. So this is the normal way that we describe this. Non-spontaneous in the forward direction. The assumption, and it is kind of the natural converse to this, is that you would assume that it's spontaneous in the backwards direction. Now, the reason why I'm kind of hemming and hawing over this is a lot of times we wait to deal with Q versus K to make sure that we're actually talking about the backwards direction. So your textbook doesn't do a lot of that. And this in part has to do with that fact, again, that they do thermodynamics before we do equilibrium. So technically, in your textbook, you don't really go backwards very much until you actually get into equilibrium. And then you're like, oh, of course you go forwards and backwards. No problem. But in general, yes, you could go ahead and make the statement that it should be spontaneous in the backwards direction or spontaneous in the reverse direction. I was like, we don't usually say backwards direction. We usually say the reverse direction. I don't really know why. Someone must think that it sounds nicer. So spontaneous in the reverse direction. So that really is an assumption that you can make. Again, usually we just don't say it that way, mostly because we get pretty set in the like, we are talking about a particular reaction with certain reactants and products. But yes, you can go ahead and make that assumption that it should be spontaneous in the reverse direction. I'm trying to think about why we don't usually say that. And honestly, I think we just don't say that because I think we get used to saying something is spontaneous or non-spontaneous, and that idea can be complicated enough as it is, without being like, okay, but it could be spontaneous if you change the temperature, which is also true. So I think at some point we're just like non-spontaneous. It's non-spontaneous. Something finally gets to just be non-spontaneous, as opposed to spontaneous, always spontaneous at high temperatures, spontaneous at low temperatures. I think part of this is just a vocabulary game where then you can finally say something is non-spontaneous as opposed to something is spontaneous in the reverse direction. But yeah, you could definitely still say that. So that at least brought us back around to thermodynamics a little bit. Yay! Thermodynamics. I really like thermodynamics. I think they're fun. Okay. Other questions so far?
No more than I can see, no, ma'am.
Okay, no worries. So what I am going to do is I'm going to go back to my electrochemistry thing, because one of the things I do like to talk about is dealing with water reactions. And part of what I'm going to do is I'm going to wind up erasing some of this, because I like to talk about there are some, so essentially, every instructor always has they usually like the way they explain things. And most of the things in electrochemistry, either I like the way I explain things, or I'm at least like, it's pretty good. It's fine. There's one thing though that I really like that I do, and I keep meaning to make sure I talk with the other instructors to see if there's a better way to do it or to see if I like their way better. But my way is pretty visual, and I like that. So I'm erasing some stuff because I'm gonna use those same two reactions that we used before. So I'm still going to come back and I'm going to use that manganese reaction and I'm going to use that chromate reaction. But what I'm getting rid of is I'm getting rid of all of the information that had to do with if it was a spontaneous cell, because essentially we're going to assume that it is non-spontaneous. That was me realizing I didn't plug my laptop in. There we go. That's better. So what we are going to do now is we are going to assume that this is now an electrolytic cell. So we are going to apply a voltage, and this is going to be non-spontaneous. And in this case, that is going to mean that it would not happen unless we force it to happen. And these are the two half reactions that we are the most interested in making happen, are the two that are on the screen. So this chromate reaction, and again, right now they're both written as reductions. So the question is, if I had these things put together, what are my products? What actually is made? So what are the products? So if these are my two half reactions, and it's an electrolytic cell, the first thing I need to do is figure out which one's reduced and which one's oxidized. Well, because it's an electrolytic cell and it's non-spontaneous, we would take a look at this and we would start off and say, well, this more positive voltage, since it's a non-spontaneous cell, is supposed to be the thing that's oxidized. Weird, I know. And this more negative voltage should be the thing that's reduced. Ew, but it's a non-spontaneous cell. That's what we're looking for. But now here's the weird thing, is the reaction that I picked actually has water in it. So we're going to assume that this is not just an electrolytic cell, but an aqueous electrolytic cell. And because it's aqueous, when I think about these half reactions, I don't just get to think about these half reactions. I also have to think about, is my, in this case, my chromium 3 hydroxide, because even though this is written as reduction, we've said that this should be the thing that's oxidized. So is this going to be oxidized? Or water? Because in an aqueous reaction, water might get oxidized instead. So what I need to do is find my reaction, which we already have, is right here. And then I have to find the reaction where water is oxidized. So like an hour ago, I sat down and was like, all right, where's my water reactions? This one way up here, written as reduction, looks like this. O2 as a gas plus 4 protons, aqueous plus 4 electrons, goes to 2 waters. Positive 1.23 volts. But this reaction is my oxidation of water reaction. Because, again, when I'm thinking about oxidation, I'm thinking about it going and being oxidized, which means this water that's currently a product would in fact be a reactant. I'm really trying to compare this guy. So the weird thing here is you're looking for water to be oxidized, but because everything on the table is written as reduction, you have to look for the water in the product side, because that's where it is. Even though we're trying to talk about what if water gets oxidized, The water part itself is in the products because everything in the table is written as reduction. Now, the thing about this, though, is I'm trying to pick which one is more likely to be oxidized. So just like when we did the iron example a little while ago, I have two different choices. I have this water reaction way up here, and I have this chromate chromium-3 hydroxide reaction down here. And I'm looking for which one's more likely to be oxidized. Because this is the game, even though it's an electrolytic cell, I'm basically just kind of throwing electrons in there, and those electrons can either get picked up by that chromium-3 hydroxide, oxidized. Those electrons can either leave that chromium-3 hydroxide, or they can leave the water. Those are my two options. Well, for oxidation, I get to pick the lower one on the table, the one with the more negative value. So between these two reactions, I expect my chromium-3 hydroxide to actually be oxidized, which means as far as my products go, I'm going to actually expect to get this chromate here. Because again, my oxidation is going to run backwards. So I'm looking for my products. I'm going to get chromate for my oxidation reaction. So oxidation is going to give me some chromate. It will not give me oxygen gas. It will not give me protons because my water is not the thing getting oxidized. So this is part of that products idea, is if the water got oxidized, we would have oxygen gas and protons. But that's not what happens. We get the chromate instead. So now I'm going to ask that same question, but I'm going to ask that question for my reduction. So, and this is also the part where I should say we can also ask this question of essentially something like what forms at the cathode. Here's the news. I don't know if it's good or bad. The cathode is the site of reduction. That's the definition of cathode. That definition does not care if the cathode is in a galvanic cell or in an electrolytic cell. The cathode is the site of reduction, no matter what. Spontaneous or non-spontaneous, cathode is the site of reduction. So I am picking between water getting reduced, and again, I could write this out to be nice and big, but now they're actually reduction reactions. So this is sometimes a little easier to see just because we don't have to think about going backwards to H2. And this one is negative 0.83 volts. And then my manganese. And these are my options for what happens at the cathode for what gets reduced. The thing is when we talk about reduction, the thing that is more likely to be reduced is the thing that has the more positive value. That more positive value in this case is not the manganese. The more positive value is my water reaction. So when I want to know what my products are, my products now are actually hydrogen gas and that hydroxide. So I can do that because I can consider my manganese compared to my water reaction. But notice I defined that water being reduced. So when I wanted to talk about oxidation, I looked for one where water gets oxidized. Then when I want to talk about reduction, I want to find one where water gets reduced. So I have to make sure I'm paying attention and using the correct water reactions. So in this case, my water gets reduced. That's negative 0.83 volts. And the thing that forms, I can go ahead and say that this is either my H2 gas. We also get base. We also get the hydroxide. We have a tendency to focus on the gases being formed just because they make bubbles and they're nice and easy to see. But those are the things more likely to happen. Now, I mentioned I like the way that I talk through this. I have to admit, everything we just did, kind of normal, kind of not that special. Here's the thing I actually really like. What I'm going to do is zoom out a bunch. So here is my lovely table. Let me make it a little bigger, but not very much. So you can still see in my lovely table those two pink lines. Those two pink lines are my water reactions. So my two pink lines are the water reactions. The top one is water being oxidized. The bottom one is water being reduced. But I got to tell you, it doesn't matter. Because what you would do, and you can actually see, well, I'm gonna make it a little bit bigger, is we were comparing one reaction here and we were comparing another reaction here. When I want to figure out what's actually happening, basically anything that happens inside of those two pink lines, anything that happens in between, in the middle of my water reactions actually happens. No water. Basically, the reactions occurring in between the water reactions are not that extreme. So they are going to be the things that happen, whether it's oxidation or reduction, I don't care which one. If they are in between those two water reactions, in between my two pink lines, that half reaction is what actually happens in an aqueous electrolytic cell. You get those actual things. Which means on the two extreme ends is where things change. So at my top end, this is water. And on my bottom end, this is also water. Now, this is the part where we have to think through this whole electrolytic business. So here at the top, this is water gets oxidized. I know it's weird, but it's true. So this is, again, thinking about that as an electrolytic cell. So the top, water gets oxidized, and at the bottom, water would get reduced instead of whatever those half reactions are. And that is essentially what we found. So even though I know it's a bit difficult to see, this blue circle here was our chromate reaction, and we compared this chromate reaction for oxidation to this top pink line and decided that what we actually got was the chromate. Then this one that's outside of my two water reactions, I got the manganese reaction, and because it's outside, it's not in the middle, it's outside of those two water reactions, the water is the thing that actually got, in this case, reduced. And so that's when we said that what forms at the cathode is that hydrogen gas and that base, because it's happening outside of those two and not in the middle. So that's the part that I like, just because I frankly think it's one of the few times where looking at the big giant chart is useful, because then we can go ahead and talk about where are my two water reactions that I care about. And essentially, if the half reaction happens in the middle, then that half reaction happens. And if the half reaction that was one of my options is on my two extreme ends, then the water gets either oxidized or reduced instead, if it's happening on the two extreme ends. So I hope that's helpful in our aqueous electrolytic cells. Other questions so far?
No, ma'am.
So in that case, I asked my class for questions, actually last Friday. So the first one, main topics are information. I think we've already covered that. Are there any equations that we must know? So this is, again, where I'll go ahead and grab that potentially useful information. You should be able to work the entire exam with this set. There is only one thing that's a little bit strange, and that's actually we can do one of those. But I think that equation is on here. So actually, I'm going to work with this thing in pink. So there is this kind of odd thing that we can do, and it sounds something like this. How long does it take to electroplate 5 grams of aluminum metal? So we haven't done this one yet. This is also in electrochemistry. This is that very, very last thing to do. So, oh, with a current of, sorry, I'm not done. Electroplate 5 grams of aluminum onto a surface with a current of 2.5 amps. There we go. Now I've got all the pieces. So this one's kind of weird because it doesn't look like the other things that we've done so far. But what this is going to do, this is still electrochemistry. Also, I went ahead and used aluminum just to be different. For any of you that have ever had jewelry of any sort, a lot of times golds or cheap gold jewelry is electroplated, which means that it is a layer of golds on a surface of something else. Super common, by the way, to have plated jewelry, mostly because that way it looks like golds and is golds on the outside, but it's got a cheaper metal on the inside. Very economical. So the thing is that we need to basically explain one more thing. That's this amps thing. This amps thing is the thing that I mentioned is actually over here, but it's written kind of strangely. This is written as 1 coulomb. Let me spell that correctly, or at least to try to spell that correctly. So it's written as 1 coulomb is equal to 1 amp times second. Personally, I find it more valuable to go ahead and do a little bit of algebra and divide both sides by seconds, so I can have 1 amp is equal to a coulomb per second, which means that this amps is actually a rate. So this is actually 2.5 coulombs per 1 second. So now, at least, the fact that we have a unit of time is what we're being asked for, and we have amps, which is in seconds, should hopefully help us out a little bit. Now, the thing though is we have coulombs. That's weird. How are we going to use coulombs? Where is that in this table? Oh, look, we have Faraday's constant. Faraday's constant is, I'm just going to write this out over here. Oh, they gave us the fancier that we're going to use the whole thing. I have Faraday's constant, which is 96,000. I'm going to use the one off of the chart, 485 coulombs per 1 mole of electrons. Okie dokie. So we can at least, so thinking about this, we're going to use forwards in a minute, but I've got something that will get me to time with coulombs. So if I have coulombs, I could get time. I can have coulombs if I had moles of electrons. This is aluminum. I could think about aluminum and the fact that aluminum has a particular reaction that I could, in fact, for every 1 mole of aluminum, I need 3 electrons. So 3 electrons will get me 1 mole of aluminum via this chart. Okay. This is progress, I promise. So I need 3 moles of electrons for 1 mole of aluminum. Great. How much aluminum did I actually need? Did it tell me? Sure did. Grams. Which means if I have 5 grams of aluminum, I need to know how many moles, or I need something that will relate grams to moles. Sounds like a periodic table time. I might have actually gotten rid of too many things. Do I have my periodic? Do I have my? Oh no. Oh, there it is. Yay. This is that time I was getting ready for this review and I was like, do I need a periodic table? Nah. Oh, wait, yes, I do. Just for this question, I need a periodic table. So I was told I have 5 grams of aluminum, and from a periodic table, I can find that there are 26.98 grams of aluminum in 1 mole. Woo! So from grams to moles, from moles to electrons, or moles of electrons to coulombs, from coulombs to seconds. Whew. Let's actually put this all together and take a look at this. So how long does it take to electroplate 5 grams of aluminum on a surface with a current of 2.5 amps? We are going to start with those 5 grams of aluminum. And we're going to use the periodic table to say that there are 26.98 grams of aluminum in 1 mole of aluminum. Then from our standard reduction potential table, we're going to say that to get 1 mole of aluminum, I need 3 electrons. Don't forget this one. This is the one that most people forget. This is your standard reduction table. This is from your periodic table. Okay, now I have electrons. Now I'm going to use Faraday's constant. And I'm going to say that for every 1 mole of electrons, I have 96,485 coulombs. This is Faraday's constant, also known as fancy F, but Faraday's constant. $96,000. Then for every, what did we say? 2.5 coulombs takes 1 second. Those are the amps out of the problem, or the current from the problem. So now we actually have a dimensional analysis problem, is really what this is. So it is using a lot of chemistry. It's using a lot of chemistry language, but this is actually all about putting together all of the pieces and all of the parts and figuring out how long this actually takes. So I get for 5 grams of aluminum. Yep, double checking all of my math. I get 2.15 times 10 to the 4th seconds. That's a lot of seconds. That's so many seconds that honestly we probably wouldn't do that. So I'm going to go ahead and say that there are 60 seconds in 1 minute. And there are also 60 minutes in 1 hour. And now I'm going to see what I actually get. That's more reasonable. This is 5.96 hours, about 6 hours, but 5.96 hours. So I will say that these sorts of problems are the kind that definitely deserve practice, just because they have enough steps in them that it can be very tempting to skip a step. The most commonly skipped step is the one from the standard reduction table, where you have to deal with the 3 electrons for every mole of substance. That one, the one in blue here, is usually the one that gets skipped. So don't stop that, don't forget that. Also, we are very well aware that that is the most skipped part. So that wrong answer is always on there. Yeah, so this does have a number of steps to it, but all the steps are there, but one of them is on the periodic table, one of them is the standard reduction potential table, one of them is Faraday's constant, which is going to be on that potentially useful information. It will be. And the other one is the definition of current, which again is also there to deal with coulombs and amps and seconds, but it's written fairly streamlined. So knowing what that is on the page is really helpful. So this is the one thing that is not really an equation. And again, technically all of the information you need to do it is on the potentially useful information page, but it's the one thing that I would say people sometimes forget or forget parts of. So again, you do need to know how to navigate that kind of a problem. So any equations we must know, just things on the potentially useful information page. I would also mention that second law of thermodynamics that we already talked about earlier today. We did not talk about the third law of thermodynamics, but that's another good thing to make sure that you're aware of. How to know when it's basic or acidic, or will the question specify? This had to do with balancing reactions. The question will specify. Question will specify. Keep in mind, the question could say that it is a pH of 5 to tell you that it's acidic. So it could give you acidic or basic without the words acidic or basic, because by this point in the semester, y'all should be comfortable with the idea that a pH less than 7 is considered to be acidic at 25 degrees Celsius, and a pH greater than 7 at 25 degrees Celsius is considered to be basic. So we could give you that information as just the pH instead of the word, but we would give you some sort of information. We have to. If you go over half reactions and combining the 2 half reactions, I did one of those. I want to solve more questions in cell potential. We did at least a little bit of that. I can certainly prepare for that for next workshop. Can I elaborate on how anions of the galvanic cell move towards the anode, not the cathode? Okay. Let's talk about that one. So when we are talking about our 2 half reactions and a salt bridge. So first of all, typically when we're talking about anions and cations moving, we're almost always talking about the things out of the salt bridge. That's almost always the thing that we are discussing, things out of the salt bridge. So if we have 2 reactions, and I'm going to grab things off of my little table to make my life a little bit easier. Yeah. Apparently I'll just delete it. That's not the plan. Table. So let's go ahead and still pick things that make some lovely solids. So we'll go ahead and pick a copper reaction, but we'll also pick a magnesium reaction. Why not? Now, because I'm going to do a copper and magnesium half cells, we're going to go ahead and make this a galvanic cell. I'm going to go ahead and write voltaic, just to get everybody used to the word that voltaic is also spontaneous. So in doing this, the one towards the top of the chart is the one more likely to be reduced. So I'm going to go ahead and write my copper 2+ plus 2 electrons going to copper solid as my reduction. And my magnesium is going to be the one more likely to be oxidized. Magnesium solid going to magnesium 2+ plus 2 electrons. So I've got my reduction, which means that this is my red cat. This is my cathode. So this is going to be the thing that is positive. Yep. Then over here on the other side, this is an ox. So this is going to be my oxidation. So this is going to be my anode. My electrons are going to move from anode to cathode because they are needed over there. My charge on my anode in a spontaneous cell is negative. So what's happening here is on my site of reduction, I have copper solid being made. So over time, I am making and I'm adding copper. So copper 2+ is forming copper solid. So the more that this happens, even though since I have copper 2+ in here, there should be some sort of counter ion. It could be sulfate, it could be nitrate. To save time, I'm just going to go ahead and put nitrate. So there's nitrate in here because that copper 2+ isn't alone. But the thing is that over time, more and more of this copper 2+ is going away. More and more of this copper 2+ is leaving because it's forming solid copper. So I only have so much copper, and over time, I lose those cations, which means I'm going to rely on cations out of the salt bridge. We'll still use KNO3. So my salt bridge is going to have potassium nitrate in it. And so because I have more of this copper 2+ being used, I'm going to need the potassium. I'm going to need the positive anions out of here, the cations, to move towards my cathode. They're moving towards the cathode from the salt bridge. So the salt bridge is allowing the reaction to continue taking place because otherwise, once I used a certain number of copper cations, this reaction, this beaker over here on the left would get kind of negative because there would just be this nitrate left over and the charges wouldn't be balanced anymore and the reaction would just kind of stop. So instead, positive cations from the salt bridge come out of the salt bridge to help replace that positive charge. Similarly, here on the left, I have magnesium, but here the solid is actually essentially degrading, and I am getting magnesium 2+ ions. So over time, this electrode is actually shrinking and it's getting smaller and smaller and smaller over time because more and more magnesium 2+ is coming in here. We'll assume that there was already some nitrate in here. Let's keep using it as a counter ion. But as we get more and more positive charge here on our anode, we're going to go ahead and get anions to balance that. So we're going to get more nitrate in this case, because I keep using nitrate over and over and over again, out of my salt bridge to go ahead and balance the positive cations from the magnesium that are coming down. So when we say things like anions move towards the anode, cations move towards the cathode, that's moving from the salt bridge. So they are originating in the salt bridge and they are helping balance the ions that are leaving the solution or that are coming into the solution from the electrochemical reaction. Any other questions out of the chat for right now?
No, ma'am. Still none.
Nope.
Okay. Yeah, so that's this notion of anions moving towards the anode and not the cathode. We're trying to balance the charges. Okay. So one of the questions, what are the variations of all the Gibbs free energy questions? So the tricky thing with all the Gibbs free energy questions is, at least by now, I've done enough things that we've finally done all of the main equations. So the difficult thing is that whenever we're talking about Gibbs free energy, we're going to be able to relate not the standard version, but just free energy, either to dealing with Q. We could also relate it, though I know this, we only gave you guys one version of which has the standard symbols in there, but we can also talk about Gibbs free energy with that. And then there's Gibbs free energy applied to the, again, not the standard. So there's a whole lot of versions dealing with Gibbs free energy and standard Gibbs free energy. So when we're dealing with standard, a lot of these equations look similar until we go to put K into the mix. So because anytime we're dealing with the standard Gibbs free energy, that's always going to relate things back to K. And that's where our standard goes. So anytime we have K, we're going to be dealing with a standard. Anytime that we are dealing with Q, we are going to be dealing with not standard. So anytime we have Q, we have not standard in there. And that really has to do with that fact that from the beginning, when we talked about Q, Q was always just whatever you had. Q could be equal to K. It could be, but it doesn't have to be. And so we always want to talk about the fact that whenever we're dealing with Q, we just have whatever concentrations we happen to have. So dealing with Q will always have extra components or extra pieces because we're trying to figure out that comparison between Q and K and what direction is our reaction actually going to go based on what we have and what equilibrium is, or where equilibrium is. I definitely understand the idea of like, gosh, that delta G and delta G standard are sure in a lot of places. I don't disagree. Don't forget, we can also just have y'all do one where you deal with products and reactants. So this notion of these using delta G of formation values. So similar to how y'all did that on the last exam with entropy, we can still do that with enthalpy, we can still do that with entropy, and we can still do that with Gibbs free energy. So just keep in mind that we can still apply any of those things all together. Trying to look on here. Has a question, how would a redox reaction look for a galvanic cell where an ion is reduced to another ion? As far as a redox reaction, again, we can grab, do I have one on here? I do, where an ion is reduced to another ion. So let's go ahead and just grab the iron one because, again, using something relatively straightforward, we'll go ahead and make that one be reduced, and we'll go ahead and use a lower one for an oxidation. So I could go ahead and use, so the goal is to use 2 ions essentially. So I'm going to use this iron 3+ plus an electron goes to iron 2+, and my zinc, in this case solid, going to zinc 2+ plus 2 electrons. Really, the only thing that this does that makes it look a little bit different is it really depends on the situation. So we'll go ahead and we'll make sure our reactions are balanced. 2 irons plus zinc goes to the zinc plus 2 Fe2+. Really, in most situations, the only time where this is going to look different is, one, when we go to do our cell notation, so because I have my zinc being my anode, being my oxidation, that's going to be zinc solid line, zinc 2+, aqueous, a salt bridge. Then here's the part where the two ions look a little bit different, because whenever we use lines, those lines are always supposed to be a phase boundary. So I wouldn't actually use a line to show off the products and reactants of the iron reaction, because my iron reaction here, they're both aqueous species. So I would use a comma so that I can go ahead and still separate to show off that I am still having my reduction reaction, my iron 3+ going to iron 2+, and those are two separate things. But I'm just going to use a comma, no line, because lines are for phase boundaries. But the thing is that because when we think about half cells, and because when we think about drawing the whole electrochemical cell, I need a place for this reduction to occur. I still need a site of reduction. I still need an electrode. I still need an actual cathode. So this is the weird thing, is I have to keep going for my cell notation, and I'm going to go ahead and add platinum, because this then is my actual cathode. This is the site. This is where the reduction happens. So since this is the site of reduction, that platinum is the actual cathode. It's the physical item where the reaction is taking place, and it's the physical item that the wire connects to. So this is kind of that weird situation where we are expecting you all to consider the fact that in electrochemistry, there are wires that connect things together. So if you're going to have a reaction occur, you still have to have some kind of wires connecting things. You don't get to just dangle stuff and be like, I'm sure it's happening. No dangling wires. Okay, your wires have to connect to something. So if you have an all aqueous half cell, there has to be an electrode there somewhere, because their wire has to connect to something. You don't just get to dangle and hang out in place. So a lot of times, so I know that I drew half cells before and kind of had like the arrow going towards it. A lot of times when I'm drawing this for this particular half cell, it would look something like this. I would go ahead and have like platinum as a solid, and a lot of times it's still a rectangle, whatever. That makes my life easier. But then because I have two different ions, mine usually looks like this. So I usually draw a curved arrow to show off my Fe3+ going to Fe2+. So that way I can still demonstrate that I still have a reaction happening here, and that reduction is taking place on the platinum. Because here's a wire going to the other half cell. Here's my salt bridge, still going to the other half cell that I didn't draw. So all of those things still need to take place. All of those things still need to happen. But those are some of the differences. So not a lot of differences, but still some difference in the cell notation, and some differences oftentimes in how we draw the half cell, just so we can put in all the pieces that are really there. So a lot of the other questions I had from my class are mostly trying to get a better handle on drawing things, a better handle on representations of things, lots of the same stuff. Since I brought it up, I will go ahead and show off the third law of thermodynamics, since I brought it up. The entropy of a perfect crystalline substance at 0 Kelvin, it does not say okay, that says 0 Kelvin, is 0. The third law of thermodynamics is valuable because whenever we talk about values of entropy, really when we're dealing with entropy, all of those values are calculated values for entropy. Entropy is statistics, believe it or not. So because we are actually calculating all of the values for entropy, we're not getting any of those from a value. We're not getting any of those from an experiment. We're doing all of those by calculations. So we talk about entropy a little bit differently. And part of how we do that is by the third law of thermodynamics. So essentially at 0 Kelvin, we're going to have such a perfect crystalline solid that it won't have any options, essentially. There will be no other energy states for that to be in. It will have one energy state to deal with and have essentially an entropy of 0. So, yeah. Other questions out of the chat?
No, ma'am.
So, give you guys some general advice. Practice does help a lot. If you can't tell, I like some of the little mnemonics. So I like talking about a red cat, like there is some sort of like furry creature with pointy ears that happens to be the color red to help remind me that the cathode is the site of reduction. I like an ox to remind me. And so then I am thinking of like the animal with the horns that looks kind of like a bull, but it's not a bull, is an ox. To remind me that the anode is the site of oxidation. I will still write out sometimes to myself oil rig to remind me that oxidation is loss of electrons and reduction is gain of electrons. Whatever helps you guys think through all of these things, I'm all for. I know this is a stressful time of the semester as we get towards the very end because it's cramming in a lot of stuff at the very, very end, but you guys can do it. Oh, I will actually end with this. So here's what I want to do. I want to do zinc 2+, lithium plus, and am I writing these in order? I'm writing these in order to make my life easier. Silver plus. So here are 3 things. And I want to ask among these 3 things, which is the best oxidizing agent? Now, this is something that's actually been on the table. So granted, as I look at this, there's a giant green arrow pointing up this way. And I did pick, in fact, silver is higher towards the top, and then zinc is towards the bottom, and then lithium is at the very, very bottom. These are all cations. When I'm asking for the best oxidizing agent, agent means that's the thing that's going to be able to accept electrons. So all of my oxidizing agents have positive charges because all of these things are able to accept electrons. My best oxidizing agent is just the one closest to the top of the table. My best oxidizing agent is my silver plus. So that one's relatively straightforward. I'm essentially looking at a whole bunch of 3 different cations and asking you what's the most likely thing to be reduced with different language. Now, here's where this question gets weird. If I just gave you these same 3 cations and I asked you a different question and I said, which is the best reducing agent? This has a much different feel because it's really tempting to tell me that the best reducing agent is the lithium plus. But the answer is none of these because a reducing agent has to be able to give me electrons. Notice that when the chart talks about increasing strength as a reducing agent, all of the reducing agents are on the right. All of the reducing agents are on the product side. All of the reducing agents, except for there's a few in here, but I didn't select those. All of those reducing agents are either neutral or negative because all of these reducing agents have to have electrons to give. if I'm picking between silver plus, zinc 2 plus, and lithium plus, these are all things that already gave their electrons away. They don't have any electrons to give. None of these are reducing agents. They can't do it. A reducing agent has to be able to give away electrons. And these basically, they already did that. So this is kind of like if you need to borrow like some spare change for some strange reason in this day and age. About the only time I can think of spare change is, I don't know if you guys have ever seen those big penny press machines. Or a really old vending machine that doesn't take credit cards, and you're like, oh no, I need quarters, I need pennies, I need change, I need physical coins. You can't hit up the people that don't have any. You have to be able to get coins from someone who already has them. If you try to get coins from the cations, they don't have them. The cations don't have electrons to give. So none of those work as reducing agents. So do just keep in mind when you're talking about oxidizing agents and reducing agents, they need to be able to do their job. They need to actually be able to do that. So while yes, the chart is useful, the chart is important, do still pay attention to, if I need a reducing agent, I need something that has electrons. If I need an oxidizing agent, I need something that can take electrons. And make sure you choose wisely. Okay. We'll do one last call for questions, and otherwise it's about 6 o'clock. So any other questions out of the chat?
No, ma'am.
Okay. All right. Well, in that case, exams on Saturday, 10 a.m. and good luck, everybody, and have a good night.
Thank you, Dr. Taylor, and that ends Gen Chem Study Session. See you all next year. Bye.